So our speaker today is Professor Emeritus Monty Marshall. He gave us a really interesting talk on astronomy some months back. He's a fourth generation San Diegan. I haven't quite understood his biography. He has two bachelor's degrees. I haven't figured out the sequence. The first one, I gather, he majored in philosophy and minored in astronomy, and I'm not sure about the second degree. Anyway, he went to Stanford and got a PhD in geology and geophysics, and he did his thesis work on a topic, excuse me, relevant to plate tectonics. He's going to tell us about how plate tectonics was developed, the theory of plate tectonics was developed, and its application to the geology of Southern California.
So this is plate tectonics in 4 parts. In the first part, I'll just talk about the early development of a controversial theory that led to plate tectonics, but the author called it Continental Drift. And then the second part is a very interesting part on how the combination of two apparently separate earth science fields led to proving plate tectonics. It's a good example of serendipity. The third part, the important consequences of the way in which the plates interact. And then at the end, some just short planning observations and questions. How much time do I have, Don?
Oh, 45 minutes or a bit more.
Okay. I think I can do that. Okay, so in the beginning, the real father of plate tectonics as it evolved was a German meteorologist, not a geologist, Alfred Wagner, who specialized in the climate of Greenland. And looking at maps of the world, he proposed in 1920 that all of the continents were once together. He could see how the outlines, especially of the circumatlantic continents, could fit into one another. And so he said that there used to be a supercontinent called Pangea, which is 2 Greek words meaning all in earth. And he called his continental dispersal continental drift. But the majority of the world's earth scientists thought for decades after 1920 that his version of continental drift was impossible. And when I was an undergraduate, to answer Don, my first degree, I majored in philosophy, minored in astronomy. I wanted to be an astronomer. I went to Villanova, and then I came back home to San Diego in astronomy, but I took a beginning geology class, and the professor was so charismatic, and the field trips were so much fun that I thought, I'd rather be a geologist, geophysicist than an astronomer. And so that's how that switch happened.
Excuse me, Monty, can I interrupt for a moment?
Yes.
Jack, I'm told that there are people who want to join the meeting who aren't able to, or I don't see any way for me to bring them in. Are you able to do that?
Oh, am I able to do that?
Is Jack?
Oh, I'm sorry, I had to step away from it. What was it you asked?
Well, I'm told that there are people who want to join the meeting who are unable to, and I don't see how to do it. I thought maybe you as the.
There is no waiting room, so if they have the correct link, they should have no trouble coming in.
All right. Okay. Thank you. Go ahead, Monty.
Yeah, they should click on the same thing I clicked on, right?
Yeah. Mhm.
And if they still can't get on, let me know, and maybe we can start from the beginning. Okay, well, in any case, in my last year at San Diego State, I remember the professor talking about continental drift, and he said it was a stupid idea. And so then I went off to Stanford, and my first year at Stanford, I began learning that maybe it wasn't such a stupid idea, and things proceeded from there. So this is a picture of Alfred Wagner in this little hut on Greenland. And he, like I say, he specialized in the meteorology of Greenland. And this is a picture of him with his Inuit guide. Wegener walked across Greenland twice, and it's over 600 miles across, and so he must have been a pretty hardy fellow. And this was a picture taken before his last hike, and a snowstorm came up, they got separated, and by the time the Inuit guide found Wegener, he had frozen to death. So he died on Greenland. So this is a picture of two versions of Pangea. The lower right is Wegener's Pangea. And so you'll notice, I'll move can everybody see my arrow?
Mm-hmm. Yes.
Yeah, so you'll notice the best fit is how the bulge in South America, Brazil, can fit into equatorial Africa. And then Northwest Africa lines up with North America. Europe lines up with North America and Greenland. Antarctica, the southern continents are down here at the bottom. That's Wegener's drawing, and the upper one is the current understanding of Pangea. It really did exist. So again, you can see the good match. Here's North America, here's Africa, South America, here's Antarctica, here's Australia, and then this little wedge-shaped fragment is India. So when the breakup happened, of all the continents that moved the furthest from this conglomeration was India. It just took off and went up and smashed into southern China. And this is a map that shows the fit of the circumatlantic continents. And so the red and blue areas are areas of overlap or gaps, but you see that the fit is very good. Geographers had pointed this out and found it interesting, and Wegener thought it was more than just interesting, but most geologists said it was coincidence. Well, it turns out there's a little more evidence than the fit.
India.
This is a map of the southern continents. The data was the best. The data for Pangea was the best in the southern continents. And in fact, when I was told that this was stupid, there were some South American geologists who didn't think it was so stupid. And so what you see here is a big green band that stretches from Australia through Antarctica, India, Madagascar, Africa, South America. And that's a famous fern called the Glossopteris. And so it's found in all those continents. But the people who didn't like continental drift said, well, you know, the fern spores or whatever they're called could be blown by the wind. And, you know, the wind could circulate those spores to all those continents.
India.
A more convincing argument is that there were 3 reptiles, land reptiles. This one right here on your left in South America. Fossils of that land reptile were found all across South America and into Africa. This little one in the upper right, Lysistrurus, its fossils were found in Antarctica, India, Madagascar, and Africa. And these are land animals, you know, they don't just hop in the ocean and go swim to another continent. So that was a puzzle, how they got distributed. The next slide shows various ways that it could have happened, and the last one turns out to be the way it did happen. So if it's a small animal, it could be carried across on a raft of debris. One time when I was flying down along the coast of South America, there was a big storm and the rivers were flooding and they were washing huge masses of trees and bushes out into the Eastern Pacific. So, you know, there probably were snakes and animals and stuff in that mass of bushes. And so that's a way of transporting small things. And then on the upper right, for elephants, of course, elephants weren't connected. They you know, but in any case, if it were a big animal, there could have been isthmus, like the Isthmus of Panama, that the big animals could have walked across from continent to continent, and then after they got across, those isthmuses mysteriously sank. Okay, well, the oceanographers couldn't find any evidence of sunken isthmuses. And then on the lower left, island stepping stones. So maybe the plants and animals didn't have to travel the whole ocean. Maybe there was just a series of islands that they could hop from one, or even maybe a little bit of raft from island to island, just the way the Polynesians migrated from Asia to Hawaii. And then on the lower right is what really happened. The continents did drift apart. So you see 2 forlorn brontosauruses, this one right here on the left, and this one over here. And I guess they were partners, and now they're crying that they're being separated. The separation, of course, took much longer than the lifetime of a brontosaurus. Okay, so the main opponents to Wegener's continental drift hypothesis were seismologists. And using seismic surveys, they found that the continental crust was 7 times thicker than oceanic crust. It extended way down below, lower in the mantle than oceanic crust did. And there was no known force that was strong enough to cause the continents to plow through the oceanic crust when the continents split up, and presumably the rest of the world was capped with oceanic crust. There was no way known of doing that. And so here is a German from the 1950s, the German data on the thickness of continents and ocean. So if you start at the left, you see how thin the crust under the Pacific Ocean is, and how thick the crust under North America and Europe is. And again, the Atlantic Ocean has very thin crust. So a simpler diagram next shows you'll be able to picture this better. See how much deeper the continental crust extends into the mantle. So just imagine what would happen if you wanted that continental crust to migrate to the right. Well, it would have to shove that oceanic crust, plow like an icebreaker plowing through ice. There should be, if this happened, there should be huge slabs of oceanic crust that are thrust right up into the air. Okay, nobody's ever seen that. And then in the rear, on the left-hand side, a big hole should open up on the seafloor as the continental crust moves to the right. And oceanographers never found that big hole. So, this continental crust plowing its way through oceanic crust really is impossible and has not happened. But in 1931, a very famous and very smart and very futuristic thinking geologist by the name of Arthur Holmes proposed that perhaps the continents drifted and may have been pulled apart by convection currents in the mantle. So in this top block diagram, you see a single continental block. You see the ascending currents. So these ascending currents could drag at the bottom of the center of this block, tear it apart into two separate continents with, in the lower diagram now, with an ocean in between them. I mean, that's how you could say separate South America from Africa. And he was very close to the truth, but people still didn't like this idea. Well, it turns out there was a boom in oceanography in the 1950s. The oceanographers like Scripps here or Lamont in New York had the benefit of the improved fathometers that the Navy developed for checking out the seafloor and detecting German submarines. And they even had the depth charges that we used to drop on the German submarines as sound sources to bounce waves off the crust mantle boundary. And so a lot of work was done in the 50s, helped by the war. And so they discovered that the sediments on the seafloor were very thin. At this time, people thought that the oceanic crust was as old as the continental, and they knew the continental crust was billions of years old. So if the oceans were billions of years old, they should have a huge layer of sediments, brought down by rivers. And so the sediments on the oceanic crust should be very thick. Well, they're not. They're just a couple of kilometers. And they learned a lot about the nature of the oceanic crust, that there's beneath the thin layer of sediments, there's a layer of basalt, volcanic rock. And then most importantly, when they towed magnetometers, they found that there were magnetic anomalies over the oceans that were unlike any magnetic anomaly on land. And these magnetic anomalies occurred in stripes that you'll see coming up. On the lower left picture, that's Maurice Ewing. He was the director of the Lamont Doherty Oceanographic Institute on the banks of the Hudson. There's a rivalry between our Scripps and Lamont as to which institution is the better. Okay, part two. So things start to change in the 60s. And that change is due to these two concurrent and apparently unrelated lines of research that I mentioned at the beginning. These converged to prove that the continents had drifted. And the two branches, one is paleomagnetism, and that's the study of the Earth. Paleo means old, study of the Earth's past magnetic field as recorded by rocks when they form. A lot of rocks, when they form, they get magnetized, and they get magnetized in the direction of the field at that place and time. And then the second thing, the oceanographers, when they towed their magnetometers around, they measured all these unusual magnetic stripes. And so the combination of these two fields broke wide open plate tectonics. And so to help you understand, these are two diagrams of the two states of the Earth's magnetic field. Look at the one on the left. You know that compass needles, wherever you are, even in South America, compass needles point north. At the equator, if the compass needle was suspended by a string so it was free to move vertically as well as horizontally, as you go from the equator to the North Pole, the needle would dip. And at the North Pole, the needle would be vertical. And then the opposite situation. So the one on the left, we call that normal polarity because that's the way it is now. But the one on the right is the reverse situation. It's when the magnetic poles flip. And so you can see the diagram on the right that everywhere on the Earth, our compass needles, if we were back at that time, would point south instead of north. So all the lines of magnetic force, the flux lines, are all reversed in their direction. So more detail. So we have the Earth's field is called the geomagnetic field. So
Oh, yeah.
in 1906, a French geologist found some rocks that were reversely magnetized. All rocks flowing out, all volcanic rocks that flow out, sediments that are being deposited now, are all magnetized the way a compass needle points now. But he found rocks that had the anti-parallel, the opposite direction. And also a famous Japanese geologist found some rocks in Japan that were reversely magnetized. But the concept that something is huge as the geomagnetic field could reverse itself at that time was inconceivable. They assumed the Earth's magnetic field has always been, has always had the polarity, has always had the direction that it has now. Compass needles always pointed north, so they thought. And so they figured, well, it must be bad rocks, that there was something in the magnetic minerals, the magnetic crystals and rocks that somehow ended up getting them magnetized opposite to the way the external field was. Well, around 1960, there were two teams of geologists, one at the U.S. Geological Survey in Menlo Park, and the other in Australia. And the people at these labs went out, they collected oriented rock cores, and they measured both the age and polarity, not just the direction like the Japanese and French did, but they measured the age of the rocks. And they discovered that all rocks of the same age had the same direction, the same polarity. which proved that it wasn't little things in the crystals, but it proved that the Earth's magnetic field had occasionally totally reversed. And they knew the time, so they were able to develop a scale that showed when the Earth's field was normal and when it was reversed. In the next slide.
In the middle of the meeting. They're not being held up. I talked to Jack about it. I interrupted the speaker and talked to Jack. I heard that, yeah. And I'm sitting,
Okay, I can hear people talking.
But Don Bamber is, because he's the host, he's not muted.
Okay.
And I think he's just chatting with his wife.
Yes.
Okay. Well, this is a picture of Alan Cox, and he was the chief scientist at the U.S. Geological Survey's lab in Menlo Park. He and two other people. So Alan, in fact, after he became famous, he moved to Stanford, and he was my thesis advisor. And I did my thesis research in that survey, the same lab that they made these discoveries, because at the time Stanford didn't have nearly as good a lab as the survey had. If you see down in the bottom of that picture, there's a little core. So these cores are only about 1 inch in diameter, and you see the yellow vertical line with the sidelines. That's the orientation line. And so before you pull the core out of the rock, you slip a piece of copper up and down along a slot, and then you fill it in with color, so you know exactly the orientation that core had before you pulled it out of the rock. Okay, so this is one of the later, what is called the geomagnetic reversal time scale. And so if you start at the top, you notice the time scale on the left in millions of years, half millions. So the Earth's field has been normal, like it is now, for most of the last 700,000 years. But when they took those cores and dated them and measured them, almost all the cores that had dates between 2.5 million years ago and 700,000 years ago were all reversed. But it wasn't a simple picture that in that reverse time that lasted for 2 million years, there were short intervals of just 10, 20, 30,000 years where the field decided to flip back to being normal again. And so the long intervals they called epochs, and the short intervals they called events. And Bruns is the French geologist who discovered reverse rocks. Matayama was the Japanese geologist who discovered reverse rocks in 1929. So they named them after famous people or famous places like Olduvai Gorge, where they collected the samples. Okay, now this is a really neat chart. This shows the development of the reversal time scale. I mean, they didn't just work it out in 1 year. So you can see up at the top, the scale as of June 15, 1963, had a normal period from 0 to 1 million years, and reversed from 1 to 2, and then back to normal in 2 to 3. So in the early days, they thought these reversals were periodic with a period of 1 million years. But you can see as you look down that chart, that simple pattern really started getting complicated. And so look at the bottom of the chart as it was known in January of '69. And you can see the intervals are very unequal in length. There's short intervals of constant polarity, and there's long intervals of constant polarity. And what does that pattern remind you of? Something you see every time you go shopping. Those magnetic barcodes, right? That tell the cashier whether it's a head of lettuce, a banana, or a box of Rice Krispies. So if the Earth's field had been regular like they thought in '63, it would not have been nearly as useful as having this barcode where no part, see, this only goes back to 4 million years, but now they have the code going back to 170 million years, and there's no two parts of it that are the same. So each stretch is a little bit different, and that's very important in putting this picture together. Okay, so now Scripps had a role. In early '60s, the Navy commissioned them to go out and do a bathymetric survey of the area off of Oregon, Washington, and British Columbia. This were Cold War years. Well, a famous oceanographer, Scripps, said, look, while we're sailing back and forth measuring the bathymetry, why don't we tow a magnetometer and just see what the magnetic field over the oceans is? People thought it was sort of silly, but go ahead. And when he made all those measurements, came back to La Jolla and plotted them up, the magnetic highs and lows weren't circles or some zigzag pattern. They were long stripes. And nobody had ever seen an magnetic anomaly pattern like that on land. So it was extremely unusual. And when I was a senior at San Diego State, we used, Bill Menard, who was the Scripps person, we used his oceanography book. I took a graduate class as an undergraduate, and we had this diagram, and he knew there were ridges and valleys in this area, and he thought, well, maybe lava flows went down the valley, and since volcanic rocks are so magnetic, that causes the black highs, and where the ridges that didn't have volcanic rocks, they were under the light colored stripes, but they didn't know. Okay, well, along in '63 came a Cambridge grad student, Fred Vine, and his advisor, Drum Matthews, and they had done some surveying in the Indian Ocean, and they found that the magnet, and they towed a magnetometer, they found that that the magnetic anomalies didn't match the topography. And in fact, they found that the magnetic anomalies look closer, they spaced out and had a pattern much closer to the geomagnetic reversal barcode than the topography did. So they said, okay, we're on to something. So, and here's the physical reasoning that they used to come up with this. And I repeat this, I'm repeating some of this, but this is really important to understand. When many rocks, not all, but when many rocks form, they acquire magnetism that's parallel to the Earth's field at the time and place they form. Volcanic rocks are especially good recorders. And the third point when a ship-towed magnetometer is towed over the volcanic oceanic crust, if that crust is reversely magnetized, that reverse magnetization is felt all the way up at the surface, and it causes a very small but detectable decrease in the strength of the background geomagnetic field. Over those stripes, the magnetometer measures a lower reading than it should, and then vice versa. If the ship sails over a strip of oceanic crust that's magnetized in the same direction that the Earth's magnetic field is at the time, those two same directions add, and you get a positive magnetic anomaly. So this is what these anomalies look like. It's a profile, it's just curves. The one in the center curves are what was what Fred Vine measured when he sailed over the same parts of the sea that the Scripps people had done some 10 years earlier. And so notice, above the line are the positive anomalies, below those horizontal lines are the negative magnetic anomalies. And then what he did is he said, okay, let's take Cox's reversal time scale. On the bottom, you see a thin strip, two parallel lines with black bands and white bands. The black bands are oceanic crust that's normally magnetized. The white part of that strip is oceanic crust that's reversely magnetized. He followed the time. He said, okay, you know, he said the seafloor was spreading from zero out, you know, going in both directions from zero, and the crust got magnetized according to the same length of those periods on the geomagnetic reversal time scale. And he could find a distance out from the spreading center where, you know, that computer modeling fit exactly what they observed in the middle. So you can compare the model in the lower diagram in the model and the observed values in the upper diagram. And so you can see it's not a perfect match, but it's very close, that you have this central magnetic anomaly that was right over the Juan de Fuca Ridge, and therefore it turned out to be a spreading center. So this is like a double-headed tape recorder. So the seafloor, the spreading to the right, records its set of normal and reverse polarities through geologic time. The oceanic crust that's forming at the ridge crest and moving off to the left, it records those same things. And so what you have is a mirror symmetry, that the curve starting at zero and going to the right is very similar to the curve starting at zero and going to the left. Not exactly, but it's close enough that people thought, uh-oh, this really is showing us that the seafloor is spreading. So here is a more concrete example of how this happens. So in the bottom part, you see a ridge axis. Basically, the Atlantic Ocean has a ridge that goes right down the center. So the seafloor expands from the center of the Atlantic, pushing Europe off to the east and the Americas off to the west. And the Pacific has what we call a rise, and I'll show you that later. But the important thing is, notice that as the seafloor spreads from the ridge axis to the right, you get the same pattern or a mirror image when you go off to the left. So this is what the crust looks like. And then up here is the magnetic anomaly that they measured. So you can really see this bilateral or mirror symmetry in these curves. The right hand is like the mirror image reverse of the left hand. Okay, so by 1968, this bilateral symmetry of the marine magnetic anomalies on either side of oceanic ridges and rises, point 1, the same pattern. They found the same pattern all over the world. Every time they crossed a ridge or a rise, they got that same pattern. Sometimes if the spreading center was fast, the anomalies were spread out further, but the pattern was the same. And so the mirror symmetry, the worldwide sameness of the magnetic anomalies, and the fact that they matched, that they were able to be modeled so accurately by the known reversals of the Earth's magnetic field, proved to almost everybody that seafloor spreading, this is just one part of plate tectonics, but it's a fundamental part, that seafloor spreading was real. And I graduated from San Diego State in '66. I went to Stanford in '66. And by '68, I picked Alan Cox as my thesis advisor, and he picked me. And so together we went to a big geophysical meeting in San Francisco. It's an annual meeting, and people for the preceding couple of years have been arguing these points about, the oceanography data from Lamont and from Scripps, and how good was the data and how perfect was the match. But by 1968, the curves were so perfectly bilaterally symmetrical, they were so perfectly worldwide that all of us in the audience, especially people like me that was told that continents couldn't spread apart. The ocean didn't have spreading center. We just sat there and said, God damn it, it's true. It's not stupid like I was taught as an undergraduate. Okay, now, that was a profile. Here are the magnetic anomalies up off of Oregon and Washington. Here's the Juan de Fuca Ridge. That's the main ridge in this area. Can you see the symmetry?
Right.
If you start at the center, okay, the red is normal polarity. Okay, it's reinforcing the prisoner's field. The yellow bands are parts of the oceanic crust, strips of the oceanic crust that are counteracting the prisoner's field. So they're the negative anomalies. Do you see any symmetry in that picture?
Yeah.
Yeah, notice the center part is really fat because the lavas there add both to the plate that's moving to the right and the plate that's moving to the left, so it's double thickness. And then you go off to the left and you see this thin one. But if you go off to the right, what do you see?
A thin line.
Another thin one. And then you go even further out and you see this sort of jumbled up mixed one. Well, you go out even further and you see this jumbled up mixed one. So
Mhm.
there you go. That's the that's the symmetry that I've been talking about. So, okay, part 3. Let's talk about the plates. So Holmes was able to solve Wegener's drift problem by having those convection currents, but seismologists in the 60s found an even better solution. They, with higher resolution seismic surveys, they found that the outer part of the Earth was different, was a little bit different than people realized before them, that the outer 100 kilometers of the Earth, and as you saw before, the continental crust is only 40 kilometers thick, oceanic crust is only 7. So basically the crust in the outer mantle down to a depth of 100 kilometers turns out to be rigid. The rocks are very strong. But from 100 kilometers down to 300 kilometers, there's a 200-kilometer thick layer of the upper mantle that's partially molten. And isn't it all strong? It's gushy. So the next slide. Okay, so now you see it, a real cross-section. Here's continental crust on the right, oceanic crust thin on the left. So the lithosphere, this 100 kilometers going from the surface of the ground down to this point is fairly rigid. Lithos in Greek means rock. Sphere is sphere, of course. But the mantle below it is partially molten. Astheno in Greek means weak. Sphere is sphere. So basically, this boundary that I'm tracing my arrow across and is denoted by a speckled surface above and a continuous brown surface beneath, that's the base of the lithosphere, and everything above it is what moves. So it's not, so unlike Wegener, it's not just the continents that move, it's the whole lithosphere that moves. So the oceanic crust can move along with the continental crust. And that's the key understanding to plate tectonics. And so plates, in the word plate tectonics, are just pieces of lithosphere, big pieces, little pieces, and those pieces are able to slide on this gushy, weak lower asthenosphere. That's the fundamental point in plate tectonics. Okay, so whoops. So this is what I just said, and so you can read it. I'll give you a couple of seconds to read it, so it will really sink in. Okay, so now let's look at the plate. This is a world plate map, and as you can see, the plate in the center is the Pacific plate. It's the plate that we're on, in fact, and it's the biggest plate in the world. There's about 12 fairly large plates, and then, you know, many very small plates, but there's 12 big ones. And so in our part of the world, we have the Pacific plate, we have the North American plate. Okay, and notice, the North American plate isn't just North America. It extends from the boundary with the Pacific plate on the west all the way over to the Mid-Atlantic Ridge. So what you see here, the North American plate is capped on the west with continental crust and on the east with oceanic crust. So these boundaries don't correspond to seashores. They don't correspond to the boundary between oceanic crust and continental crust. Plates can be entirely oceanic crust, like this little plate down south of us off of Central America, the Cocos Plate, or the bigger plate that's being subducted beneath South America called the Nazca Plate, named after that place with the Nazca lines. And the symbols on this, the lines with shark's teeth are subduction zones. So the Nazca Plate is diving down beneath South America, and I'll show you a slide of that in a second. And that Nazca Plate, when it dives down, it causes the volcanoes of the Andes.
Volcanoes in the Andes?
Yeah, the Andes, you know, are a string of volcanoes all the way from up here in, not Ecuador, but the country that has all the oil, all the way down to Chile. And then the Pacific Plate, notice it's moving off towards the northwest, is it dives beneath the Philippine Islands and beneath the Japanese islands and beneath the Aleutians. You see little barbs there because in the Western Pacific and the Northern Pacific, the Pacific Plate is diving beneath those continents and causing chains of volcanoes on the other side of the Pacific. So the Pacific Ocean is called the Ring of Fire. That's where the majority of the Earth's volcanoes are. Okay, now, since we know those anomalies are caused by reversals, and the reversals have been dated, we can now tell the age of the seafloor. The Miocene time started around 26 million years ago. Pliocene time started around 5 million years ago. Well, if you take a ship-towed magnetometer and you go out to the 5 million year old magnetic anomaly, you know that down on the seafloor, you're at the boundary between oceanic crust that was created in the Pliocene and the oceanic crust that was created in the Miocene. So just with a ship-towed magnetometer, you can tell the age of all the crust in the oceans. And so, I mean, that's just amazing. In the early days, they would have had to go and drill a bunch of holes all across here to find that out. And they have drilled holes all across the Pacific. I was on one of the drilling cruises, and holes all across the Atlantic just to prove that, to verify that this map is right. And so you can see the oldest part of the Pacific seafloor is that part off of Japan. And so it's currently being subducted right now. So some million years from now, that upper Jurassic blue patch of seafloor will be eaten up and subducted down beneath Japan. Okay, now something else that's really great is the modern advent of GPS, the global positioning satellites. You know, people could tell from the magnetic anomalies the plates were moving, but that was over time frames of millions of years. But GPSs now are so accurate that over a time period of 10 years, if you put a GPS station, you anchor it down in cement and stuff like that, and you just let it record the latitude and longitude for a period of 10 or 20 years, you can see how that piece on the Earth's surface has moved. And so all these red arrows show that. The length of the arrows show the velocity, and the base of the arrows, say this arrow right here near the Great Lakes. So that point up in Canada is moving towards the west-southwest. Whereas if you went off here to Labrador, that point is moving to the west-northwest. And if you went down here on Australia to one of their GPS stations, you can see that point in Australia is moving very quickly to the northeast. So this is really neat now. We can tell the exact direction and velocity, speed that these plates are moving. So with that data, you can come here to this East Pacific rise. That's the equivalent, that's the spreading center in the Pacific. You notice it's not in the center like the Mid-Atlantic Ridge. It's off on the eastern part of the Pacific. So you can see that number 13.4. So the Pacific plate is moving away from the Nazca plate, you know, as magma comes up and, you know, it's a spreading center. Those two plates are spreading apart from one another at the rate of 13 centimeters a year. 13 centimeters, there's like 2.5 centimeters in an inch. And so this is like five inches a year. If you were to stand in that Rift Valley and put your feet on either side of a central crack, in a year, your feet would be 6 inches further apart. Okay, so now what can plates do? Well, they can do three things. They can diverge. When they diverge, they cause rift zones and spreading centers. They can converge or come together. And when they come together, if one of the plates is an oceanic plate, it'll dive, and the other continental, the oceanic plate will dive down beneath the continental plate in a process called subduction. Or if the leading edge of both of the plates are capped with continental crust, continental crust doesn't like to dive down, and so the two plates just collide in a collision zone. And the best example of that is the Alps in Europe and the Himalayas in Asia. And the third motion is the plates can just slide past one another. The best example of that is our own San Andreas Fault. So an important point is that all three kinds of these plate interactions involve faulting. I mean, things are sliding past one another, either horizontally or along an inclined plane like the subduction zones. And where two rock masses slide past one another, they can't do it smoothly. Friction holds the motion back until the stresses build up to the point where the two plates jump ahead, 1 inch, 1 foot, 10 feet. And of course, the more they jump ahead, the larger an earthquake is caused. So that's the origin of earthquakes, is rocks sticking and then slipping. Subduction zones and collision zones are the areas that cause the greatest, the highest magnitude earthquake. Seismometers came online around 1900, and I think the largest earthquake in the last century and up until now occurred in Chile, and it was little more than a magnitude 9, and it was caused by the subduction of the Pacific seafloor beneath Chile. And then volcanoes are associated with subduction in a very important way, and diverging margins like we've talked about. You open up a space and the lava comes up. Okay, so now let's look at examples of these. So here you have a single plate. You have a plume of magma, that red blob beneath the center of the block. You have the arrows showing that that plate is being stretched. The right-hand side going to the right, the left-hand side going to the left. And so initially the crust is thinned and rifted. The best example of this is that line of ridges and valleys in Nevada and Utah called the Basin and Range. Well, it stopped at that point here in the United States, but if the stretching continues, that land will, the crust thins so much that the elevation of the land drops down below sea level. That area is flooded by a linear sea here in the third panel. And then if it keeps on going, all the continental crust is moved away. And now when the magma comes up, it forms only oceanic crust. So this is a diagram of what happened to move Africa away from South America. So, or the mid-Atlantic, that ridge is that mid-ocean ridge in the bottom panel. You could label that the mid-Atlantic ridge. Okay, and then this is a detailed view of the seafloor. So you can see magma coming up from down here in the mantle. It accumulates in a big magma chamber in the lower crust. These green dots are crystals that crystallize out from the magma and settle to the bottom of the liquid magma chamber. But then some of the lava comes up through narrow cracks and flows out on the ocean floor. When that lava hits the cold seawater, it doesn't flow like a lava flow on land. Instead, it produces a bunch of lumpy, bumpy blobs called pillow lava. And so the next slide shows you what those salt pillows look like. You can see this must be fairly close to the spreading center because there's only a little bit of white sediments that have accumulated on top of them. This was the area of my research. I collected fragments of pillow basalts from scripts. I measured their magnetization, and it turns out because they cool so quickly, the magnetite grains in these rocks have 10 times the magnetization of if that lava flow had been up in the air. And so this layer of pillow basalts is a big contributor to the magnetic anomalies that we've been talking about. Okay, so now what about subduction? So this is subduction. This is a great example of subduction offshore of California. So just imagine you're standing at the Mexican border looking north, and the seafloor is diving beneath the western margin of North America. And you can see what happens when that oceanic crust and the lithosphere reaches a depth of about 100 kilometers. The water in the sediments that it's dragged down with it, as well as all the clays and the weathered basalts, the heat drives water out of those sediments, and the water fluxes. It causes the mantle to melt. And so you see these plumes like hot air balloons ascending up through the upper mantle, congregating at the base of the crust, and then continuing on up to make big magma chambers close to the surface. If any lava continues on up and reaches air, it forms a volcano. So this is very pertinent to our mountains. Our mountains, there used to be volcanoes. There are no active volcanoes in San Diego County, but there are remnants of 100-million-year-old volcanoes. Mount San Miguel is one, Dictionary Hill is another one, Del Cerro is another one. So San Diego County used to be covered with volcanoes, and then which overlaid these magma chambers. Well, in 100 million years, almost all of the volcanoes have been eroded away, and erosion is now down into this magma chamber, and that magma chamber is crystallized to form the granitic rocks of our peninsular ranges. So when you drive out past El Cajon and see El Capitan and all the rocks of our mountains, they all formed down at this depth, and erosion has brought them to the surface. And that's true of the Sierra Nevada, and it is still true of the Cascades, because remember, off the coast of Oregon and Washington, that Juan de Fuca plate is still diving down. So that's why Northern California and Oregon and Washington still have active volcanoes. There's still subduction going on up there, but it's stopped down here. Now, something you don't see in this picture is this is the ocean crust offshore of San Diego, okay? The name for this plate that was diving down that caused our mountains was the Farallon plate, after the Farallon Islands off of the Golden Gate Bridge. But further out in the Pacific was another plate, the Pacific plate, that you saw, the great big plate in the center of the Pacific Ocean. Well, as the Farallon plate was subducted, it went down faster than the Pacific plate was spreading from the Farallon plate. So the Pacific plate was drug east and into contact with the North American plate. So here's a diagram that shows that. So it all started about 30 million years ago. Up to 30 million years ago, see this line with the shark's teeth? That's subduction, okay? But at about 25 million years ago, this edge, this corner of the Pacific plate slammed into the coast near Los Angeles, and the Pacific plate then was connected to the North American plate. And so now in this second panel, you see there's still some of the Juan de Fuca plate up north, the plate to the south, the Cocos plate is there, but between the R and the M, here the, sorry, my mouse is new and my thumb keeps pushing the wrong button. See this stretch between R and M with the arrows pointing in opposite direction? They're the two plates. The Pacific plate and the North American plate are sliding past one another. There's no tendency for the Pacific plate to subduct, they just slide past. And so this is the proto-San Andreas. This is the beginning of the San Andreas fault. And then at 10 million years, you can see what happened. More and more of the Pacific plate came into contact. So the M migrated north, the R migrated south. So now this whole stretch is the Proto-San Andreas. And then at 5 million years ago, the Pacific plate tore the Gulf of California away from mainland Mexico, and the modern San Andreas was born. And it extends from the Salton Sea up, it goes offshore. The San Andreas Fault is several miles offshore of the Golden Gate Bridge, and it plays touch with the coastline all the way up to M, and M stands for Cape Mendocino. So now the next slide is not a slide. It's a video made by Tanya Atwater. She is she's like the mother, the mother of plate tectonics, or the mother especially of California geology. And she was at UCSB. She's retired now. And so she has devoted the last few years to making models, videos of these things. So I will play this several times. It's only like 20 seconds. The first time I won't say anything, just look, and then the second time I'll make comments. Pretty neat, huh? Okay, now I'll play it again and just point out some things that are happening. Okay, first contact. Okay, near Los Angeles, you have so now the Farallon plate is separated into two parts. The Juan de Fuca plate is a remnant of the Farallon plate to the north. The Cocos plate is a remnant of the Farallon plate to the south. Continuing on. Okay, so you notice the Gulf of that Baja California is starting to be pulled away from mainland Mexico. So this is a nice real-time video of West Coast tectonics, plate tectonics. Okay, final part, and this is short. How much time do I have, Donald? Have I used up most of my time?
Yeah. Well, if you're quick, let's get through this, and we can then open up for questions.
Questions. Okay, yeah, this is very quick. Just 2 observations and 2 questions. Plate observation 1. Plate boundaries are broad and not just a single line on a map, you know, as you normally see, or a simple fault. They're a congregation of faults. And then what forces drive the plates? That's changed a little bit over time, and I'll show you a diagram showing you the 2 things. And then the question, has there always been plate tectonics? The Earth formed 4.5 billion years ago. Was there plate tectonics from the get-go? Or, as many people think, plate tectonics didn't start until 3 billion years ago instead of 5 billion years ago. And maybe modern plate tectonics, the way it's working now, maybe only started 1 billion years ago. These are subjects of argument in the geologic community. Okay, now to show you how broad these zones are, look at the seismic zone here on the left-hand side on the west coast of South America. So as this plate, remember it was called the Nazca plate, is diving down beneath South America to cause the Andean chain of volcanoes, it can rupture shallow or it can rupture deep. So, you know, there's this broad, all these dots are earthquakes. So you can see that the boundary between the Nazca plate and the South American plate is not just a single line. And then if you go up into the Mediterranean, you have Africa smashing into Europe, all kinds of earthquakes. And then, of course, the big ones for China, especially for China, is as India smashes into southern China, that collision zone is a very broad zone of earthquakes, which are very dangerous. When I first came down to San Diego State, there was an earthquake that killed like 200,000 people in China, in one of the cities in China. Okay, and then I'll go through this real fast. People always used to concentrate on convection cells. Where the convection cell came up, that was the spreading center. Where the convection cell went down, that was the subduction zone. But now they say, look, these ridges are 5 or 6 or 7,000 feet higher than the deep sea floor to either side. So they stand higher, so gravity pulls is part of the reason why plates pull apart, the oceanic plates pull apart. And then the slab that goes down is denser than the mantle rocks on either side because it's cold. It's been up there under the ocean for tens of millions of years, so it's cold and dense. So just it sinks because of its higher density. It's called slab pull. Okay, that's the end of the talk.
Okay, thank you. That was great. I was impressed with all the graphics you put together. It's you really put a lot of work into this.
Yeah, I did. Hours and hours and hours.
So, do you want to end your screen sharing and we can start with questions?
Yeah, so I just stop share?
I think so, yeah.
Okay. Ah, okay, I can see you and some of the other people.
Yes, and if anyone wants to ask a question, they should use the raise hand feature, which on my window, I see it at the bottom. It might be elsewhere on other people's computers. So if you have a question, click on raise hand.
Yeah, I'm open to any questions that I can answer.
Well, let me ask a question then.
Okay.
I seem to recall reading once that part of the evidence for the spreading apart of the continents was that the layers of rock on either side of the Atlantic Ocean they occurred in the same order. Is that correct? And did Wegener notice that, or was it someone later on?
No, that's something that I should have mentioned, that not only are there fossil connections, but across the Atlantic Ocean especially, you can find rocks in Brazil that match the same rocks, identical rocks in equatorial Africa. And then as far as the United States, it's very interesting because when people, this is modern times now, when people studied the rocks in the Appalachians, they found rocks in the Appalachians especially in Florida, that came from Africa. And that when Africa, was connected to North America and then pulled away, Northwest Africa left pieces of itself along the East Coast.
Okay, thank you. Kiki Lindblade, do you want to ask your question?
Sure, yeah. Well, I have one about that whole fossil thing. I think I read someplace where when they were digging the Panama Canal, they found a fossil of a hippo. It was part of that shield kind of effect there in northern South America. So I thought that was just very cool. One of the questions I had kind of goes back to the Permian extinction. With all of this, I'm wondering, they talk about the fact that there may have been some kind of event because it was so quick and so profound that like 95% of all oceanic life disappeared. Is there any evidence anywhere of where, I don't know, excessive amounts of lava have, piled out or anything like that?
Yes. There have been about 5 major biological extinctions in the Earth history. And the Permian Permo-Jurassic extinction is a Permo-Triassic, extinction is one of the largest, like you said. And there is a huge, and I may get this mixed up because, the most famous extinction was the dinosaurs.
Right.
And, and now it's pretty much agreed that it was a 15-kilometer wide asteroid that smashed into the Gulf of Mexico. But it turns out there's a series of lava flows, I think the Deccan traps in India, that are about the same age. And so there's some people who adamantly think that all the carbon dioxide and sulfur gases that come up with basalts played a role in that extinction. And then as far as the one you're referring to, there's an area in Russia, and I think it's Siberia, that has many hundreds, thousands of square miles of lava flows that date to that Permian extinction. And if you've ever been to Hawaii, you'll know that the rangers keep you away from some of those craters that have bubbling magma in the bottom of them.
Understandably.
Yeah, because not so much, because there's carbon dioxide coming out, which won't hurt you unless that's all you breathe. Herds of sheep on the sides of volcanoes, in valleys on the sides of volcanoes, have died when that heavy carbon dioxide fills the valley and there's no oxygen for the animals to breathe, and so they die. But then even worse is the sulfur gases that when they combine with water turn into sulfuric acid. One of the modes, or one of the possible causes for the Permian extinction is lava flows with all the sulfur gases in particular.
Thank you.
Yeah.
Hey, Jane Takahashi, do you want to go ahead with your?
Okay. 2 questions. Number one, you said that the activity in Southern California has dissipated. But my question is, what about the activity in the Salton Buttes, and where does that play? And then number 2 is, what is I was looking this morning at Japan, where they're going to put up a seawall because the beaches are being inundated, and the question is, how great of an effect is global warming and to the change of our Earth as we know it?
Okay, for your first question, yeah, I didn't say that things have slowed down in Southern California. Subductions stopped even, well, say 30 million years ago. And then strands of what is called the Proto-San Andreas formed offshore. But at around 5 million years, when the Gulf of California really started opening, the present San Andreas was created. The fault jumped from offshore to the Imperial Valley, and the current San Andreas extends from near the south shore of the Salton Sea all the way up to Cape Mendocino. And in terms of things being quiet, it is true that the southern San Andreas has been the quietest of all the strands, all the way up to San Francisco at least. You know, there was a big earthquake near Los Angeles in 1855, and the San Francisco earthquake of 1906. But the San Andreas in the Salton Sea hasn't ruptured in like 300 years. And so they don't know why it's taking so long, because the average interval between earthquakes on the San Andreas is 125 years. But you have to be real careful to emphasize and underline the word average. It's sort of like those magnetic reversals. You know, you can have two reversals 10,000 years apart, and then the next one may not happen for 200,000 years. And so the same way with earthquakes, you can have two bad earthquakes 50 years apart and then not have anything for a couple hundred, but then when you average them, it comes out to 125. And the people at Scripps have some ideas about how the weight of the water, or the water in the Salton Sea, may be delaying the rupture on the southern San Andreas, but it's delaying it. It's not preventing it. And so one of these days, the people in Palm Springs and out there in the desert will really be shaken up. And we'll feel it fairly strong here too, but not as strong as the people in Palm Springs. And then to your second question, sea level rise. Yeah, the Japanese, you saw what happened in the tsunami of, was it 2009?
Fukushima?
Yes. Well, that the tsunami went over the seawall up in northern Japan and flooded, did a lot of damage, washed a lot of homes away, and then it ruined, you know, those nuclear reactors near Tokyo. So that's one thing that they want to build higher seawalls for. And then just because of the tsunamis, but then sea level rise is coming in, and that's a lot slower. But I've been down in the Marquesas Islands that are atolls where the highest point on the island is 6 feet above sea level. And when all the ice in Greenland melts, which it's well on its way to do, sea level will rise 20 feet. So downtown San Diego will be submerged, and those all the people on the atolls in the Marquesas will have long since moved somewhere else.
Okay, if there are no further questions, let's thank the speaker.
Thanks very much.
That was a great talk. I really enjoyed it. So we'll end the meeting now then.
Okay, yeah, thanks, Don.
Thank you.
Yeah, you're welcome.
Thanks.
That was like
Thank you.
the clearest explanation of that I've ever heard. So,
Oh, thank you very much.
Well, thanks, Monty. This is Ralph Britton. We met each other in Argentina and just enjoyed your lecture. I now live in Los Angeles or in San Diego, and perhaps we'll see each other.
Yeah, sometime when things open up a bit, let's get together for dinner.
That would be good. We can do
Yeah.
that.
Okay, thanks to everybody.